So, brief introduction. Who are Carbon TP? You can see up there. We're an energy transition advisory firm focused on the hard-to-abate sectors. We do a lot of work with a lot of industrial clients. I'm not going to go into a lot of that now, but if anyone's interested, I'll be happy to chat to you over a beer later on. One thing we've learned in our time in this industry and in sort of trying to figure out how to decarbonize industrial assets is that Plexos is uniquely positioned to be the decision-making tool of the energy transition. And that's what I'm going to talk about for the rest of this presentation. So, optimization of emissions-intensive industrial assets within energy ecosystems. I spent a long time trying to summarize what this presentation was about and get a sort of a bit of a soundbite, and that was unfortunately the best that I could do. But what does it actually mean? From our perspective, the energy transition, more than any period ever before, requires optimization of systems. It no longer works to build an industrial asset in a location with the view that you are going to take a constant, stable supply of energy, fuel, and other inputs and run that asset flat out 24/7, 365 to maximize the capital utilization and minimize the unit cost. And the question, why? Well, because as we transition to variable renewable power supplies, the sweat the asset approach is not the maximum capital utilization at a system level or the minimum unit cost. When you look at an integrated system with a large percentage of renewables, the total capital cost of the system is what needs to be optimized, and the system needs to be operated very differently to minimize cost. The same goes for modifying existing assets with a view to decarbonizing them as well. So what do we mean by emissions-intensive industrial assets? These are the bedrock of modern society, producing the commodities that we use in vast quantities to build our infrastructure, generate and transmit power, and increase crop yields to feed our populations. And they are all energy and emissions intensive, with high throughputs typically and low margins. They are also complex, capital intensive to decarbonize, and highly cost sensitive as a result of the low margins. Just a factoid for the day on the subject of ammonia, which is not what we chose to look at, but also quite interesting. It's estimated that more than half of the total nitrogen in human tissues today, which is crucial for DNA and protein synthesis, has been artificially supplied via the Haber-Bosch ammonia process rather than natural nitrogen fixation. So this is like just an indication of how important these industries are to our way of life and survival. But we didn't look at ammonia. We chose to focus on steel as it is one of the largest single sources of global emissions and one of the hardest sectors to decarbonise, and also because the South Australian government asked us to. So, if we take a quick look at steel production, the byproducts are CO2. Primary steel is currently produced by two main routes, of which by far the most significant is the blast furnace and the basic oxygen furnace. In a blast furnace, you take iron ore, mix it with coke, which is basically pure carbon, at a very high temperature, and the carbon reacts with the ore to form iron and carbon dioxide. Additionally, you produce slag, which contains the unwanted impurities that were present in the iron ore, together with some residual iron metal and iron oxides. In the basic oxygen furnace, which isn't illustrated on this slide, that's the second stage of the blast furnace, limestone, oxygen, and alloying elements are added to remove residual impurities and condition the steel. And the end-to-end process releases around 2.3 to 2.8 tons of CO2 per ton of liquid metal produced. So very emissions intensive, but also highly essential commodity for modern life. The other primary steel production route is the direct reduction furnace, which is shown on the right of this slide, which is coupled with the electric arc furnace, which again isn't illustrated here. In this process, you take iron ore of a very specific quality, you grind it up into a powder, concentrate it and pelletize it before loading it into the DRI furnace. Typically, the reduction reaction is achieved by using natural gas, which contains both carbon and hydrogen, actually proportionally quite a lot more hydrogen on a molecular basis than carbon. The pellets don't get hot enough to melt in that reaction, and the product of the DRI reactor is called sponge iron, which is pellets that have had the oxygen removed, leaving a metallic iron pellet which has got voids throughout it where the oxygen once was, so it's kind of like a sponge, hence the term sponge iron. Unfortunately, because iron is a reactive metal and that pellet has an incredibly high surface area because of all the voids in it, they tend to spontaneously ignite, so you can't do a lot with them in that condition, and so they do what's called briquetting and actually compact that while it's still hot and turn it into hot briquetted iron. The byproducts of this are CO2 and water vapor, so the water vapor comes from the hydrogen, and this significantly reduces the amount of CO2 that's released when compared to a pure carbon-based blast furnace. The HBI pellets can then be fed into an electric arc furnace and typically are blended with scrap, steel, and electricity is provided to melt the pellets and scrap and produce new steel. And so you can see that the energy or emissions intensity of this process actually is highly dependent on the emissions intensity of electricity in terms of the arc furnace. But also, when it comes to decarbonising this, the natural way to do that would be to replace the gas with hydrogen. As you already have a significant portion of hydrogen, you can actually replace it all with hydrogen to decarbonise it. So how does Plexos actually come into this? Because we talked a lot about other stuff, but not much about Plexos. Okay, so here's a sort of an illustration of a model that we built. This doesn't show all of it, but these are the key components. So our goal was to build a model that could be used to explore the optimum configuration of a green steel asset under various different sets of input assumptions. Using the universal library in Plexos, we can model a DRI furnace and all of the supporting infrastructure in a single system model, and then explore how the optimized configuration changes as we vary input parameters and constraints. Essentially, Plexos tells us the optimum system configuration and how to operate the individual assets to achieve the minimum production cost for any given set of input data and constraints. Input data can include capital costs, fixed and variable operating costs, operational constraints, feedstock costs, operational performance curves, etc., etc. We've not illustrated the whole model here, as the page would have been far too busy, and in fact we actually went well beyond this, included hydrogen compression, desalination and water treatment, air separation, which supplies nitrogen and oxygen to the process, and this captured the majority of the large-scale capital items and investment that will be required to build a DRI facility. So if we now just talk about the HBI and forget about steel manufacturing, just to keep things relatively simple, some key questions looking at this might be, what is the optimum balance of hydrogen production capacity and storage for a given annual HBI output? How does this change if we allow the DRI plant rate to flex up and down? And traditionally, industrial assets have not been particularly flexible, but if you can make them flexible, what's the benefit? And what is the overall impact of that on the cost of iron produced? What is the impact of putting this plant in a different location with different renewable resource characteristics and different grid connection capabilities? When renewable electricity is not available, if I keep the electrolyzers at a minimum output using gas-fired electricity to save putting them through a shutdown cycle, how does that impact the overall emissions intensity of my product? Alternatively, can we build the electrolyzer degradation into the model and get Plexos to decide what is the best operational strategy and configuration based on an emissions intensity constraint? Clearly, there are a huge number of variables and potential optimizations in configuring a plant like this, and getting it right will be worth tens, if not hundreds of millions in reduced capital costs and ultimately reduced unit costs of production. And let's not forget that these are high throughput, low margin commodities, so every single cent counts. To provide some context around the financial scale, the total investment required for a 1 million tonne per annum renewable and green hydrogen-based iron manufacturing facility would be in the order of 10 billion Australian dollars. So a configuration optimization that saves even only 1 to 2% capex is worth 1 to 200 million. But how do we make sense of this? So using the Plexos XL add-in for the cloud, we're able to pull down data from multiple model runs to compare different scenarios with different sets of input conditions and operational constraints. We can use that data to build a set of output charts relevant to whatever we want to see. Here we have compared some key cost metrics across 4 different scenarios we modeled for the hydrogen-based DRI plant. From this, it can be seen that allowing the production rate to flex, which is represented by scenarios 2 and 4, results in significant cost reductions across all metrics. Remember at the start, we said the run it flat out 24/7 365 paradigm has shifted. This is the proof. But this also tells you exactly how to shift it to optimize for lowest possible cost. In a world powered by renewables, capital costs and operating strategies will be defined by the renewable resource profiles and operational flexibility of the core production assets, together with the capital and operating costs of those assets. For example, an asset in a location with great renewable resources might not end up with a lower production cost if the capital cost of developing infrastructure are higher. But access to lower cost feedstocks or presence of the right geology for lower cost hydrogen storage could actually tip the balance and make that more cost effective. All of this variability can be expressed in a Plexos model to understand the optimum for a specific location, how that stacks up against alternative locations, and bring focus to the primary areas driving cost. We can use the Plexos output to deep dive and explore the reasons behind what we're seeing. For example, what is driving the much higher power cost in scenario 1? We can see that in scenarios 1 and 3, where iron production rate is fixed, the cost of power generation is higher. Digging deeper into this reveals it's due to a number of reasons. Unsurprisingly, overbuild of renewables tends to be greater when there is no flex in demand, with more of the renewable generation curtailed. Additionally, although not illustrated here, the solar capacity factor in the first location is approximately 20% higher than the second location, which offsets some of the curtailment impact and is why the unit solar cost in scenario 1 is actually lower than scenario 3, even though the curtailment is higher. So you can see that we can basically pull any information we like and actually do some serious financial modeling and analysis out of the back of the Plexos modeling and Plexos outputs. Interestingly here, the wind capacity factors in both locations are similar, but it turns out that the timing of the wind generation in the second location is far more complementary to solar, with the wind primarily blowing overnight. And so again, you can pick up these kind of like subtleties and understand, where it makes most sense to build your asset in the context of what you have available to you. Finally, it's worth noting that we get more gas generation capacity built without a flexible load to plug the occasional gaps in renewable generation. But the utilization is very low, leading to a high cost of generation. But there's still more to the energy price story, as so far we only looked at power generation costs and not actually delivered power. So here we've been looking at what's coming out of the renewables, but we haven't looked at the cost of power that's actually being delivered to the operational assets that are going into producing the steel. And to do that, we need to take a look into storage. Looking at the storage aspect, the answer to this lies in how much battery capacity gets built. In spite of the first scenario having a lower battery unit cost, it adds more to the delivered power cost, and it turns out that 25 times more battery capacity was built in scenario 1 than scenario 3. Again, reason for that, scenario 1 is very solar heavy compared to scenario 3. Scenario 3 has that complementary wind-solar profile, so it doesn't need to build as much storage. It can actually just build more wind, which supplements that. So the answer lies, as I said, in the renewable resource profiles, driving scenario 1 driving a majority solar battery solution, whereas scenario 3 is more balanced between solar and wind. So far, we've only looked into one aspect of the cost, but the Plexos output contains all costs and can be configured to provide meaningful comparisons that focus the attention where it's required. For example, batteries and hydrogen infrastructure account for a large portion of the overall cost. Varying the cost and performance of any one of these components is likely to have a major effect. But wouldn't it be great if we could explore every combination to find the optimum? With the Plexos scenario function, we can do that, running as many models as we need to find the optimum. Even without further model runs, clear insights from this overview are that it makes sense to invest in improving flexibility in the core underlying asset, as this has a massive impact on overall CapEx. And whilst the location in this instance has a lesser impact, there's still a potential $100 million of CapEx saving by building in location B versus location A. And that translates into a lower cost product and higher profitability. The unit cost breakdown not only shows us which options result in lowest overall cost and hence which is likely to be the most profitable option, but also shows how that cost arises from the various inputs to the process. And this includes both capital and operating costs. There's almost no limitation as to how these costs can be broken down, providing the appropriate input data is in the model, and there is also no real limitation on the number of scenarios that can be explored, especially using the cloud environment to run multiple models in parallel. And you know, we can think of just innumerable scenarios and situations where you can optimize this. For instance, if I buy a cheaper electrolyzer that is less efficient, is that actually beneficial or not? If my electrolyzer has better turn-down characteristics, but I can't actually turn it off, you know, how does that impact my overall cost of steel? There's so many different permutations and combinations of this, and each of them has the potential to have tens or hundreds of millions of dollars impact on the overall cost for the integrated system to produce green steel. And the same goes for other assets. You can take this approach and apply it to alumina, you can apply it to aluminium, you can apply it to any of the big industrial processes where there's a degree of complexity and they're hard to decarbonize and they are also very energy intensive. And effectively, you know, we believe that Plexos is kind of like the future of the concept select stage of industrial assets, and also in terms of, you know, decarbonizing existing assets, just due to the fact that you can co-optimize across multiple constraints and variables, including financial constraints, emissions constraints. You can model all of the emissions in here. We did it in this model as well, so we know exactly how many emissions are coming out of each of these scenarios, and get really deep techno-economic insights to support optimized decision-making when it comes to spending capital in a decarbonizing world. So that is the end of my time. I'm pretty much bang on the 20 minutes there. I've got 10 seconds left, but there's also a few minutes left for questions. So if anybody has any questions on this, on the universal model, on how you integrate the Excel into the cloud or any of the other modeling, then please ask away.
Thanks for the presentation. This is Gabriel from BHP.
Hi.
Being in BHP, we're quite interested in the whole green steel topic.
Yeah.
One slide before, on your profitability slide, it's two questions I have. One is, you demonstrated in the earlier slides about how...
Sorry, which slide?
Oh, it was just one, your last slide just before the key takeaways, profitability.
Okay.
Oh, that's it, yes.
Sorry, that one?
Yeah.
Yeah.
You explained in the slides prior to this that you could save quite a lot of money in scenarios 2 and 4 by allowing for the flexible, by adding flexibility aspect to it. It's interesting that $1 per ton difference between two. I would expect the $1 per ton to actually have a much bigger difference. Is that because also the tons have reduced?
No, the tons are the same in every scenario. So the $1 per ton difference, don't forget you've got operating costs in this as well. So that we were looking at CapEx, but this is also OpEx. So this is dollar per ton out of the back end. You have got a fairly significant difference between 1 and 3 and 2 and 4. So that's where you're allowing the flexibility, yeah? So I think you're saving around $100, $200 a ton of iron or steel. The difference there that's shown is the difference between the two locations. So that's one thing which was interesting coming out of this, is that allowing flexibility in the steelmaking process kind of levelizes the differential between different locations. So when you look at scenario 1 versus scenario 3, there's a fairly significant difference in cost. So one location is clearly better than the other. But then once you start allowing the DRI plant to turn down and build some flexibility into the asset, you actually kind of levelize that cost differential fairly significantly. So whilst I think as it's 3, it still looks better, it's not by anywhere near as much. But what's interesting as well is that the configuration of that asset compared to the scenario, sorry, it's 2 and 4. So the configuration of the asset in scenario 4 is completely different to the asset in scenario 2, just due to the nature of the energy supplies available, but they achieve quite similar cost outcomes.
So even though the DRI is lower, the tons output of steel is the same?
No, the DRI is not lower, sorry. The DRI, so each of these are configured to produce 800,000 tons a year of DRI.
Okay, sure.
So it's basically, it's a 1 million ton per annum plant. In scenarios 1 and 3, you're forcing it to just run at a straight, flat 800,000 tons. So basically same rate every day.
Yeah.
And then in scenarios 2 and 4, you're allowing it to flex between its max output, which is 1 million tons per annum equivalent, and its minimum, which is like 50% turn down. So it can basically show up now. And with sort of, particularly when you've got seasonal variation, that flexibility in plant output makes an enormous difference to the amount of storage and renewables and other stuff that you have to build.
Okay, thanks. I thought the flexibility meant reduced overall tonnage, but
No.
it's same overall.
It's being forced to make the same amount, but it's being allowed to do it in a different way.
Sure, thanks. My last question is, how does this dollar per ton compare against traditional methods of producing steel?
In cost?
Yes.
This is way more expensive.
Yeah.
yeah. No, absolutely. I mean, this is like I think $300-400 a ton more expensive. So one of the things that comes out of this is that we are not going to decarbonize steelmaking without subsidies, legislation, regulation, or carbon taxes, or all of the above. The only people that are going to be able to afford this are going to be the car industry, because the cost of steel in a car is a minimal component of the overall car cost, and sort of white goods manufacturing, where, again, like the steel shell of white goods is a minimal cost component. So anywhere where the steel is a relatively small cost component of the overall product, this won't be a problem. But when you're talking about reinforcing bar and steel structures, and where steel is the majority of the cost, then we've got a problem.
Yep, thank you.
But you already knew that because you work for BHP. Anybody else? No, either clearly I've explained it so well, everyone gets it all perfectly, or I've explained it so badly that no one understands it and they're just like, oh. Okay. There's one more.
Yeah, I was just wondering where some of the difference in capex costs between the running the plant flexibly versus not are coming from. I don't have any idea. I'm not an engineer, but I thought it would be interesting to know.
I mean, some of it is overbuild of renewables and the amount of storage that it builds. So if you force it to use the same amount of power every single day, and particularly where you've got seasonal variability, then you're having to massively overbuild to provide that power during the period of the year when the renewables are not producing as much. And so your investment in the renewables and storage assets is very high. And this is where you know, flexibility and understanding this comes into it. But then the other part of it is as well, is that between different locations, that capex is massively redistributed. So in one case, it builds an enormous amount of solar and batteries because the solar resource is really good and that's the cheapest way to get the power that you need. Whereas in another case, it builds a lot more wind and less batteries. And then also you've got the trade-off between, because you know, you're using hydrogen to decarbonize the steel. So, and hydrogen you can store. And actually storing hydrogen is cheaper than batteries. Even though storing hydrogen is really, really expensive, it's still on like a unit energy basis cheaper than batteries, at least at the moment. And so then it's kind of like the trade-off between how much battery capacity you build and how much hydrogen storage capacity you build. But when you're storing hydrogen, you have to compress it. And so you've got a compressor in there, and it's like compression capacity. Compression is really expensive. And so, you know, this is a seriously complex problem with like a huge number of variables, and the only way to actually make sense of it and get to an optimized solution is through like the linear optimization and actually building a model. And yeah, I mean, when you start like digging into these problems and trying to understand what Plexos is doing and why it's doing it, you really opens your eyes to exactly what's going on, and also how different the different solutions are. Just by tweaking one small thing, you can come out with a very different solution. And it can make, as I said, tens, if not hundreds of millions of difference in the capital cost of the overall system.
Does anyone else have a good question? Oh, that's cool. Yeah. 1 minute. One final question. Obviously, this is a lot of complexity. Right?
Yeah.
And in the energy transition right now in Australia, it's a bit of a hot topic button as to whether or not the transition is going to make things cheaper or not. Mm-hmm. And obviously the answer sometimes is things cost money, right?
Yep.
What would you say is the message that you would use to cut through some of this complexity when you're talking to the average person?
I think, you know, it's from an industrial perspective, when you're looking at these commodities, my sense is that it's not going to be cheaper, it's going to be more expensive. Steel is going to be more expensive. Aluminium is going to be more expensive. You know, I mean, because aluminium traditionally has been, aluminium smelters have been built next to coal-fired power plants, and they've been, you know, churning out 24/7, 365 electricity at $50, $60 per megawatt hour, and that's what you need to make aluminium at the price that it currently sells for. Or not now, because the price has just flown up. But so I think, yeah, you know, like, and so it's difficult, and you know, I think that's not going to be a popular message, but you've got to trade that off against the cost of not doing this and how much it would cost if we don't do the energy transition and the impact of, you know, massive global disruption to food supplies because of climate change and other things. And I think there's been a lot, I mean, I haven't done it myself, but there's been a lot of analysis done. I've done a lot of reading around the subject that the cost of not doing the energy transition in the long term will far outweigh the cost of doing it. The problem is that the cost of doing it is like immediate and tangible, and the cost of not doing it is distant and intangible. And so, you know, I mean, it's hard enough sort of trying to convince people that they need to save for their retirement, let alone that they need to spend, or that we as a society need to spend trillions of dollars now to save multiples of trillions for future generations. You know, that's kind of like the trade-off.